through it casually at this, coming up this weekend, for example, just to kind of get a sense of what it is that is in there. But it introduces this issue of Fourier transforms. And it's a formal way of moving from the time domain to the frequency domain. And so really that's what we're, so Fourier, and it's basically moving from time to frequency and back and forth. And really, this is what we've been doing since day one, intuitively. And this is a formal mathematical methodology. And so I'm going to, and it's really beautiful. And I thought long and hard about whether or not I could do this justice in just a couple of lectures. Because I don't want to do it. If I did it the traditional method, the traditional way, it would take a long time, and it would confuse, I think. And so I convinced myself, and you guys are guinea pigs in an experiment, but I convinced myself that I could actually give you some valuable background and a useful introduction to this subject, and we'll see. I mean, I don't know, but I'm hopeful that we can. So that's what we'll talk about. We'll begin that today, and then we'll continue on that on the next 2 Mondays. This week we're doing a little bit of a business perspective, and we'll probably do a similar one next Wednesday and Friday, and then I'm saving the last day for an overview or review of what we've done in the course. I will certainly get out notes from the classes to you well before then. Anytime I don't send you something, please feel free to shoot me an email and ask for something, or if you think I'm not giving you something, then don't be shy. And then, I've met with a couple of you on Zoom, and I thought those went really, really well, one-on-one. I'm also would be happy to do one on a small group. If you have any questions or you want to go over some things that maybe you watch the video, maybe you watch me, you watch the video again, and there's still some things that you want polished. And really, I'm here, and I'm really delighted to meet with you on Zoom and see if I possibly can help you out. So what we'll do today, and we started this last time, but I was kind of not pleased with my performance on this part of last Monday's lecture, or maybe last Wednesday's lecture, and so I wanted to go back over it, and I thought I would just go ahead and do it from scratch. But we're back to one of our favorite circuits, and it's so deceptively simple. It's just 2 elements, a capacitor and a resistor, and the capacitor has a frequency dependence on it. And if I can go between time and 1/time, time and frequency, then it also has an impact on the time response of a circuit, of a voltage coming into this. And so we looked at, when we looked at this with complex impedances, what we really did was we looked at it in the frequency domain fully and from start to finish. And so now what we'll do, and actually this is the harder part of the problem. We'll actually go back to today and in classes to come, and we'll look at this RC low pass. Here's the most important word, filter, and we'll look at this in the time domain. And so what I'll do is I'll start labeling an I in, I'll start labeling an I out that flows through the resistor. I've got an I sub C that flows through the capacitor. I've got some sort of V out across the resistor, but notice the V out is actually across both of the elements, because these are a resistor and a capacitor. These two circuit elements are arranged in parallel. And so now I'm just going to write down some of the things that we know about this circuit, or these circuit elements. For example, I know that I out is equal to the current that flows in the resistor, which is V out over R, which is really just equal to V over R. So that simplifies one of our variables, is just to recognize that the voltage across here is also the same as the voltage across here is also the same as the voltage across here. And then the other piece, the other circuit element is the capacitor, and Q is equal to C times V. Now, what's hard about what we're about to do is if I need to move from the charge to a current, then what I need to do is I need to take a derivative. And so my Kirchhoffs current law and my Kirchhoffs voltage law are going to have derivatives in them. And so the equation will have derivatives in it. And that's just a simple fact of the algebra and applying the physical law. But unfortunately, what that does is that means that we have something called a differential equation. And the mathematicians remain convinced that you need to have a full course of taking derivatives, another full course of taking integrals, and then you can learn something about differential equations. And I vehemently disagree with that. I think if you know a little bit about derivatives and you maybe know a little bit about integrals, then you can solve at least a few differential equations. And so, right or wrong on my part or the mathematician's part, we will in fact treat differential equations in this lecture and next. And I'm totally aware that you haven't had a formal course in differential equations, or maybe you're taking it now, and you're still a little you're not confident yet. But again, I think that familiarity, just seeing something, again and again, and maybe with my rather casual presentation of differential equations, maybe that actually demystifies some things, and maybe you'll be stronger going into your final exam in differential equations this semester, or next semester, or the semester after that. When you see them, you won't be all stressed out or as scared. This remains a very, very low risk, fun class as far as I'm concerned. I don't want to give you more stress. If anything, I want, by doing it this way and in this style, I want to de-stress things for you. And again, if I tell you, if you see the word differential equation written down on my slide and you get all nervous about that, well, that's a great reason for you to shoot an email to me, and then we'll talk through it in more detail on a office hours, a scheduled office hours. All right, long prelude, long preface to what we're doing. But what I want to do is I want to move from this charge, and this equation here fully describes the physics of what a capacitor is. In other words, a charge produces a voltage. A charge produces a voltage. So let's go there for just a second. A charge Q implies a voltage. Now, what that voltage is, what the specifics of the voltage are mediated by the geometry and the material. Okay, so if I have charge that's arranged in a certain geometry and a certain shape, and if I have that charge in air versus in wax versus a polymer, those things matter. We're going to get a different voltage distribution depending on the shape of the charge and depending on the material that I have. Now, one of the things that I want to note for you is engineering design chooses shape and material. So we get to design our capacitors. We get to design the capacitors. We get to design the capacitance. We get to design some of the way a charge produces a voltage. Okay? So the capacitance is a function of the shape and the material. Okay? Has anyone studied capacitance in a physics class, either in high school or in college?
I have.
Do you remember a formula? Is this Emma or Laura?
Yeah.
Do you remember a formula for a capacitor? Anyone?
Q C is equal to E epsilon naught kappa area divided by distance.
Yep. Yep. So you did it actually really nicely, because you defined the material in terms of epsilon naught, and I use the word epsilon r for your kappa. And I really like that, because this is a fundamental constant, and this is a simple scaling factor that is really just between 1 and 10 for all intents and purposes. But let's take a look at this epsilon a over d, which is an example. And Emma, do you remember the shape that this is describing?
Parallel plate capacitor.
Isn't that a fancy word for a piece of metal, another piece of metal, and then some filling inside of it? Like one of those cookies that you have some biscuits on the outside and you've got some filling on the inside. And this filling is described by the dielectric constant, the epsilon. And the distance of the plates are separated by distance, and the area of that metal up top is the area. And the only reason I'm bringing this up is A, you may have seen this simple formula, epsilon A over D, in a physics class. And B, it gives you an example of what I'm talking about, which is the geometry is A over D, and the material is the filling, the epsilon. So there's nothing else in this. There's nothing else in this capacitor, in this structure, or in this number C, except for the geometry and the material. And as long as that doesn't change with respect to the voltage, then it's just a constant. The material epsilon is not going to change as a function of time. And it's hard to imagine without really working it hard, it's hard to imagine an area or a D changing as a function of time. Okay? So we're going to say that C is a constant. And therefore, Q is equal to CV. The current, I in the capacitor, is the rate of change of that charge. And if I take the d by dt, I'm going to do this a little bit more carefully than I did last time. I'm going to take d by dt of the right-hand side, and the capacitance is a constant, so I can pull that through the derivative. So now I have I in the capacitor is equal to the C dV dt. And so now I can start to write now I can start to write Kirchhoffs current law with an I in and a contribution for the current that flows to the output, and a contribution for the current that flows through the capacitor. And so I'll have I out is equal to V out over R, and that's equal to I in minus C dV dt. So this is Kirchhoffs current law, and it tells you that the input current is balanced, splits into two components. One goes through the capacitance, and one goes through the resistance. So if I can rewrite this. dV dt plus 1 over RC times V. So I'm dividing through by capacitance. And collecting the terms. And that's going to equal IN over C. And this is that much feared differential equation that I warned you about. Okay. Any questions or worries or comments right so far? Okay. One thing I want to do is I want to sketch this. I want to, well, yeah, I want to sketch this for you actually. This is a little complicated, but I think it's worth doing, and I think it's kind of interesting to do. In over C is equal to dV dt plus 1 over RC times V. And I want to write this, I want to draw this and so the IN, this by the way is our actually let me not do this yet. I'll do this and I'll do this later. I don't want to, I've got momentum here and I want to keep, I'll just keep going on this here. Okay, so I won't do the signal flow diagram. I did it last time. And so if you're curious, you can kind of look at that. I may go back and rederive it later today or next week, but this is perfectly fine for us today, right now. So there's the only way you solve a differential equation is you guess the only way you solve a differential equation is that you guess the solution. Gosh, this happened to me before. All right, 1 second. Technical difficulties here. My screen locks up on me every once in a while. Not 100% sure how to fix this other than I'll stop share. I'm gonna close that out, restart it. Okay, let's see if I can, let's see how, okay, seems to be okay now. So the only way to solve a differential equation is to guess the solution. And you know, we really mean that when we say that. The message that's often lost, that message is often lost in a classroom, because in the limit of time that we have in the classroom, we always guess the right answer. We always guess the right answer, and that's sort of a shame, because it always seems like magic when we solve a differential equation in class, and we always guess the right answer. And I really understood this better when I was in my graduate studies, when I was writing my dissertation, when I was working for my PhD. I derived from physics of the laser that I was studying. I derived a formula. I derived a differential equation, and that differential equation had never been was new, because the operation of the laser at that regime was new. And so I never, it was a brand new differential equation that had never been solved before. And so I didn't need to do it, but I wanted to see if I could come up with a nice, simple solution to it, a closed form solution to it. And so I walked around Portland, Oregon for months in my spare time, on weekends and so on. And I had a notebook, and I had an eraser, and I had a pencil. And I guessed, and I guessed, and I guessed, systematically, carefully, with some degrees of freedom. And eventually I solved it. But it really emphasized to me that there is an absolute guessing process that goes on to solve a differential equation. There are very few techniques. There are very few techniques that really get you there. Zach, what do you got?
Are some people better at guessing than others when it comes to that?
Some people, let me, I guess, Zach, I'll tell you that I was better at guessing after 6 months than I was after 1 week. So I think it's a learned skill. Samir?
I was thinking, so this equation that you've shown us, in order to figure out IN, you know, differential equations, the differences between I out and IN is a differential equation.
Yep. Yep, that's right. And what we want, the quantity that we want, Samir, is this voltage. We want to understand what the voltage is doing as a function of time. Okay? And this term here is the forcing term, or the input to the equation. Okay? Called a forcing term. Zach, do you have another question? Your hand's up. I don't know if it's just up or it's, okay.
Honestly, this seems like an advanced differential kind of problem. I'm not gonna lie, because it seems like I'm not sure exactly, maybe with more steps, but it seems complicated just in the look of it.
Yeah, so let's break it down, right? This, and so actually that's kind of a good segue. So in order to guess, we try to categorize it. And one categorization that we have is it's dv dt plus 1 over RC times V is equal to IN over C. Let's write down some things that we can observe. Here's the derivative. And it's first order. So it's not d2v dt squared, it's just dv dt. This here is a constant, and it multiplies what v of t is. And here is the input or the forcing term. Okay? So those are some of the descriptions. Those are some of the adjectives or observations, Samir, that we can get, so that we see it's not necessarily as hard as it first sees. The only thing that's hard about this is the derivative. You're not used to seeing a derivative embedded in an equality. But as I pointed out, F equals ma. Well, this guy is a derivative. This is equal to d velocity dt. It's equal to d2x dt squared. So I could come up with just another variable for the rate of change of the voltage with respect to time, like we did with F equals ma. But you know, there's no need to, and I'll show you that. So the first thing we do when we see a forced differential equation, the first thing we do is we set the forcing term equal to 0. So we first solve unforced. Differential equation. And Samir, that makes it a little bit simpler, doesn't it?
Yes, sir.
And that's just the technique that we use. And I'm going to wrap all this back together for you, Samir, and everybody. I'm going to wrap all this back together so that you have a much better picture of where this prescription for solving differential equations actually comes from. So I now have the unforced equation, dv dt plus 1 over RC times V equals 0. And I want to guess V of t. And what I'm going to guess is it's going to be some sort of a voltage e to the minus alpha t. Okay, this is just a guess. So I'm going to guess an exponential form. Now, we know about complex numbers, and so alpha might actually be complex, maybe, maybe not. And if it's complex, then we know we have a sinusoid in there. If it's not complex, I know I have a nice decaying exponential. And this is for units, because I have volts on one side, I've got volts on the other side. And so now if I take d by dt of e to the minus alpha t, does anyone know what I get? Come on, somebody should be able to take the derivative of the first derivative of an exponent. No? Well, minus alpha, e to the minus alpha t. Does that look familiar to anybody? I don't believe you. I think some people should recognize this, unless I made a mistake. Wow. Is it true that no one's taken taken derivatives before? Really? Okay. Wow. I knew some of you might not be in calculus yet, but I thought some of you would be. Zach?
So you're saying something's wrong with that answer?
Pardon?
So you're saying something's wrong with that answer?
No, I think it's right. I was just wondering.
Oh,
If,
okay. I thought you were saying that's wrong. Never mind.
no, Zach. Have you taken a derivative before, Zach?
Yeah, I'm in Calc 2.
Okay. So are you all right with the way? So could you would
Absolutely, yeah. You use the chain rule, you know.
yeah, and so you pull down this alpha in front of it and this. So Zach, do you agree that this is the derivative?
Yeah, that's what I got. You do f prime of g of t times g prime of t, whatever.
Yep. And alpha is just a constant, so it just pops down. Perfect. Yeah, I think there's just some dust in the memory, and that's why it's always we compartmentalize things too much in our presentation. If you learned it in calculus, you know it should stay in calculus, but in fact you learned it in calculus so that we can apply it in here. So if my equation is dv dt plus 1 over RC times V, then I have a minus alpha e to the minus alpha t plus 1 over RC times e to the minus alpha t. And then the question is, does that equal 0 for all time? For all time, does that equal 0? So guess V is equal to e to the minus alpha t, I guess times V naught. So I guess I need a V naught in here and I need another V naught in here. So I can go through and I can divide through by that V naught. I can multiply through by e to the positive alpha t. And I have minus alpha plus 1 over RC is equal to 0. And you'll note no time dependence in this equation. Samir, do you see that? There's absolutely no function of time in this equation.
That is, yeah, I see you. But how could you eliminate? E?
So I multiplied through by e to the positive alpha t.
Okay.
I was wondering why, when you took the derivative, did you not also bring down the t from the exponent?
I think Zach put it right. He applied the chain rule.
I'm just wondering why the chain rule wouldn't also apply to t. Is it just because it's like time? I'm not sure.
Yeah, I'm taking the derivative with respect to time, and when I take the derivative with respect to time of an exponent, this t stays put.
Okay.
You know, I think the formal way to prove that, and I'm not going to do it, is to go back to the Taylor series definition of the exponent, and then you take a term by term derivative, and you notice that you get back the same series multiplied by the constant. So that's sort of the formal, that is the formal proof, and you might actually imagine yourself doing that. Okay, so when I eliminate the time dependence, this is the definition, what I mean by solving a differential equation, is that this equality holds for all time. And that's what I mean by solving a differential equation. And that's probably something that's not emphasized enough in your math classes. And what this also means is my degree of freedom, my alpha, is equal to 1 over RC. And so my final answer is the solution to this differential equation is a V is equal to V naught times T to the minus RC. And this V naught is set by the initial condition of the circuit. So let's go back to the circuit and think physically about what's going on. If there is a charge there's an initial charge on the capacitor, charging it up to a voltage V naught. So I start with a fully charged capacitor. And then what happens is that charge trickles out the charge trickles out of the capacitor and goes through the resistance. Time is it? Okay. So this initial condition, the one that we use to set the voltage, is comes from the initial charge on the capacitor. It trickles out. So over time, I've got a nice decaying exponential, and the 1 over E point is at T equals to RC. And do you remember the role of RC when we were looking at this circuit and we were drawing its response function, its transfer function? We had a nice RC time constant. And so we have exactly the same RC time constant for exactly the same circuit. Now, my very last point that I want to bring up with you is, where does V naught come from? And it comes from a short, sharp kick of the circuit. So a delta function as the forcing term so if I put an I in, it's a short, sharp delta function. Out comes the response that's V naught e to the minus T over RC. So I can draw my graph. The delta function of T input, and then H of T equal V naught e to the minus T over RC. So physically, initial conditions come from a delta function input. Okay? And that, believe it or not, is an excellent place to stop because I've derived the time-dependent response of one of our old familiar friend circuits, the low-pass filter. Okay?